Let's move on to incidence versus prevalence. Prevalence is the total cases in the population at a given time, divided by the total population at risk at the same time. The population at risk includes only people who could be afflicted by the disease. For example, if you were trying to quantify the prevalence of endometriosis in a community, only women would be included in the population at risk, since men are not at risk for uterine diseases. The total number of cases include both new and old cases. Prevalence describes a single point in time. Incidence is slightly different. It is defined as the number of new cases in a population over a given time period, divided by the total population at risk during that time. Thus, incidence describes new cases that occur in a time period, while prevalence describes all cases at a single point in time. So, when calculating incidence, people who are not at risk for acquiring the disease are omitted. This includes people currently with the disease, as well as people previously with the disease for conditions that cannot be acquired multiple times, like the chickenpox. Roughly speaking, the prevalence is approximately equal to the incidence times the disease duration. Thus, for chronic diseases like diabetes, the prevalence will be greater than the incidence because there's a large number of existing cases. For acute diseases like the common cold, prevalence is approximately equal to incidence because almost all cases are new cases. Let's review what we discussed earlier regarding quantifying risk. I'll also introduce a different way of thinking about and calculating the various risk parameters by using a handy 2x2 risk factor versus disease table. Do you remember what type of study uses the odds ratio? Case control studies. The odds ratio is formally defined as the odds of exposure to the risk factor in the disease group divided by the odds of exposure to the risk factor in the non-disease group. More simply put, what is the likelihood that a person with disease had a certain exposure? If the exposure is a potent cause of the disease, then we would expect the odds ratio to be a number much greater than 1. Looking at the 2x2 table, we can see that the odds of exposure in the disease group is given by A, people with both disease and exposure, divided by C, which is people with the disease but not the exposure. Now, the odds that the group without disease was exposed is given by B, who are people without the disease but with the exposure, divided by D, people without the disease and who have not had the exposure. To calculate the odds ratio, these two groups are compared by division. When we simplify, these terms rearrange to A times D over B times C. Recall that the odds ratio approximates the relative risk if the prevalence of the disease is not too high. Here's a quick flash quiz. What type of study uses relative risk as a measure of association? That's right, cohort studies. The relative risk is formally defined as the relative probability of getting a disease in the exposed group compared to the unexposed group. It's calculated as the fraction with disease in the exposed group divided by the fraction with disease in the unexposed group. From the table, we can figure out that the relative risk is calculated as A divided by A plus B, which represents the fraction of disease in the exposed group with the risk factor, over C divided by C plus D, which is the fraction of disease without the risk factor. So relative risk reduction is directly related to relative risk. It's the proportion of risk reduction that is attributable to the intervention as compared with the control. Relative risk reduction equals 1 minus relative risk. For example, let's suppose you're on the Titanic and you're giving out life jackets. If 20% of passengers who have life jackets drown, whereas 80% of passengers without life jackets drown, then the relative risk is 20 over 80, or 0.25, whereas the relative risk reduction is 0.75. The relative risk reduction of drowning with a life vest is 0.75. Welcome back. In colloquial language, we often use precision and accuracy interchangeably, but they mean very different things from a statistical standpoint. Precision is the consistency and reproducibility of a test, and is also sometimes referred to as reliability. In contrast, accuracy is a measure of how close test measurements are to the true value and is sometimes referred to as validity. So, a precise test may not be accurate, and an accurate test may not be precise. Let's look at some examples to illustrate this concept. Let's say you're throwing darts at this bullseye. Whoosh! 6 darts, right in the target. You missed your bullseye, but the average is still in the center. So over the course of 6 darts, you have a lot of variation, but the average is on the money. This represents accuracy, but notice there's high variation in the dart locations, and none are in the center. Okay, let's try again with a new handful of darts. Whoosh! Okay, nice work. You were just listening to me and decided to say, hey, I'm going to make sure I have less variation in my shots. So now your darts are tightly clustered, but in the wrong spot. This is very high precision, very little variation, but low accuracy, because you didn't really hit your target. Okay, let's try again. Well, bam, bullseye. The darts are tight and centered, so are both accurate and precise. This is the goal of any test. Finally, this last diagram would be something what my attempts at dart throwing would look like. Widely scattered, totally off-center. So data corresponding to this test is neither accurate nor precise, and definitely not winning any dart games. Random error is basically the enemy of precision. It reduces the consistency and reproducibility of a test. So here's your accurate and precise test under the influence of random error. On the other hand, systematic error reduces the accuracy of a test by consistently skewing results in a particular direction, and thereby reducing the validity of the test measurements. Would look something like this. Time for another practice question. A new rapid and portable salivary glucose meter for diabetics measures a patient's salivary glucose concentration to be 200, 201, and 198 micromolar on 3 independent measurements. Using a gold standard measurement technique, the same saliva sample is determined to have a glucose concentration of 150 micromolar. How would you describe this new device in terms of accuracy, precision, and error? The answer is D. This new device was consistent in 3 independent measurements, so it's precise. However, its results are more than 30% higher than the gold standard measurement, which means it's not very accurate. A precise but inaccurate test would exhibit significant systematic error.